All right, so I'm back here in the lab. I've got my water sample here from MW2, and I kind of rushed it over here. Of course, I'm not very far away. And the reason that I rushed it is because this sample is going to start to have changes. After I pull it out of the ground, the temperature starts to change. Things about it are going to start to change. So I need to work quickly. The first thing that I want to measure here is I want to get the water temp. Obviously that's going to change after I pull it out of the well, after I pull that sample out. And along with getting the water temperature, I'm going to go ahead and get the dissolved oxygen concentration. And as it turns out, that will also change as I pull that water out of the well. For one, if the temperature changes, that affects the solubility of oxygen. And for two, because I have this little bubble in here, there might be oxygen either volatilizing out of the sample or diffusing back into the sample. So fortunately, dissolved oxygen is very easy for me to measure. I have a dissolved oxygen probe right here. This is much fancier than what we would have had if we stuck with a multi-parameter probe out in the field. So that's one of the reasons I wanted to come back. This is called an LDO meter, and it actually emits light at a certain wavelength, and based on the absorbance of light in the sample, it calculates a dissolved oxygen concentration. So very, very nice probe right here. Not something I'd want to drag out into the field and risk getting damaged. But all I have to do is I've just got to plop this. Let me unscrew the sample here. Okay, so I've just got to plop this in here. It's got a little flapper on here where I can turn this on. It'll actually spin my sample. And I might do that for certain analyses, but I don't want to spin it up because that's going to cause more oxygen to diffuse in here. So I'm just going to drop it in here. And I'm going to wait until this probe says stabilized. And then I'll read out the concentration and the temperature while we're working on it. And I'll quickly write those down in my notebook. So it says stabilizing. All right, so we got a concentration. We are at 7.77 milligrams per liter. And we have a temperature of 16.6. Some interesting numbers for us. So let me write that down before I forget. Temperature of 16.6 degrees Celsius. And a DO concentration of 7.77 milligrams per liter. Okay, so we have dissolved oxygen concentration, we have temperature. The next thing that I quickly need to measure is I need to measure the pH of this sample, because the pH is likely to change when I take the water out of the ground and start letting it react with the atmosphere, for instance, and start letting the temperature change. So I'm going to use a lab pH probe here. It's a pretty simple device. It's got a glass bulb on the bottom that allows protons to diffuse through it. So if the pH is high, protons will diffuse into the probe. If the pH is low, protons will diffuse out of that glass bulb, out of the probe. And the concentration of protons in the probe will create an electrical signal, which is translated into a pH reading with this pH meter here. Now I've already calibrated everything. I've got my colored solutions here if you've ever worked with a pH probe before. This is really no different. It's just a little bit higher end than what you might have out in the field. So to get this ready, I just need to remove the cap that has storage solution in it. And I'll spritz this down with deionized water. And since this is a liquid junction pH probe, I actually need to open this small cap right there. Okay, so now the probe's ready to go. I am going to go ahead and actually measure 50 milliliters of my sample. It doesn't really matter how much sample I use for a pH analysis. In fact, I could dunk this straight in here. But I'm going to quickly follow up the pH measurement with another measurement that does require a certain volume. So 50 milliliters, easy enough for me to measure with a graduated cylinder here. Try not to spill any of this precious water resource. Okay, I'm at 50 milliliters. Bottom of the meniscus, right at 50 milliliters. I'm going to pour it into a small beaker here. So I got graduated cylinder going to my beaker. The white thing that you see in the bottom is actually, it's a little stirrer. It's called a magnetic spin bar. And I'll go ahead and put this sample onto a stir plate. So this stir plate, I can turn it on. I'm not going to do it right now, just not this second, but I will in a second. I can turn this on and it will spin around that little magnetic spin bar and it will stir my sample for me. But I don't want to do much stirring because this sample is not at equilibrium with the atmosphere. It's been in the ground. So if I start stirring, there's a pretty good chance that I'm going to start to pull CO2 from the atmosphere into the sample. And the more CO2 that I dissolve in this sample, the more carbonic acid that I'm going to make, and the pH will actually drop. So CO2 plus water will make a small or a weak acid called carbonic acid and affect the pH. So I'm just going to drop this in here. I'm going to use the arm to help me put this probe in here. Okay, there we go. So it's in here. I just need to wait for this sample to equilibrate. It says pH stabilizing. And this actually might take a little bit. I'll go ahead and tell you while we're waiting. The groundwater doesn't really have very much dissolved in it at the Glen Sebastian Nature Trail. It's almost like rainwater, more or less. So without having a lot of ions dissolved in there, the rate that the pH meter actually adjusts to that sample is going to be pretty low. So it's going to take a while. It might take 30 seconds or so. So I'll probably just go ahead and fast forward until we get a stabilized reading. Okay, so the pH is finally stabilized. It took about a minute or so, but we are actually at a pH of 6.26, which is slightly acidic. Now, we'll talk more about this in a lecture, but that's not surprising at all. Rainwater is going to be naturally acidic because of CO2, and really there's no sort of sediment in our area that's going to cause that pH to rise. So there's nothing that's going to buffer that sample, in other words. So no limestone or carbonates or anything like that. Now, speaking of buffering, I do want to measure what's known as the alkalinity. And the alkalinity is an indication of how well buffered the sample is. In other words, how resistant to pH changes is that particular sample. So alkalinity has to do with, in many cases, how much bicarbonate is dissolved in the water, the bicarbonate coming from rocks like limestone, for instance, carbonate rocks. I just mentioned we don't really have limestone here in our sediments, so we don't really expect to see much alkalinity. In fact, we're going to do a titration here using very weak, very dilute sulfuric acid. And the alkalinity is measured based upon how much sulfuric acid I have to add to this sample to get the pH to drop down to 4.5. So we're starting at 6.26. Got to see how many drops of this very weak sulfuric acid I have to add. And I think you'll be surprised, I don't have to add much at all. In fact, I've got to be really careful when I titrate this sulfuric acid, because if I open this stopcock on the burette, there's a pretty good chance that if I add more than a couple drops, the pH is it's basically just going to drop down to 3.5 or something like that. So really low. So in other words, I don't expect there to be much alkalinity. I've done this test a number of times. But to do the alkalinity test, I will go ahead and turn on this spin bar. So I'll just turn it up. Might have to adjust it a little bit. Oop. And just move it around till it's centered and it's not banging up against the glass or the pH probe. There we go. And maybe do a little bit better job here. There we go. Okay, much better. So I have very weak sulfuric acid in here, what we say 0.02 normal sulfuric acid. So long story short, for every milliliter of sulfuric acid that I add, that's going to equal 20 milligrams per liter of alkalinity measured as calcium carbonate. Okay, so the equivalent of adding 20 milligrams per liter of calcium carbonate, which gives us the carbonate, the buffering per milliliter that I add. So let me just very slowly, I'm going to have to keep one eye over here, one eye on the burette here, this 25 milliliter burette. And actually I can see as soon as I turn this spin bar on, the pH has already dropped down to 5.34. So it's already pulling in CO2 from the atmosphere, making it more acidic. So I'm just going to barely add the slightest drop here. And I got to be really careful and do this drop by drop. Okay, 1 drop has been added. 1 drop has been added. I see the pH has already dropped below 5. It's at 4.77, 4.74, 4.68, 6.5, 6.4, 6.3, 6.2, 6.1, 5.9, 5.4, 5.2, 5.1, 5.0. That's it. That's all it took for us to crash the pH from 6.26 to now it's still going. It's at 4.38 right now, and it's dropping. So in other words, there's essentially no alkalinity in this sample. But the best that we can do based on this instrumentation is we can go down to 1/10 of a milliliter. Remember, there's 20 milligrams per liter of calcium carbonate per milliliter. We added 1/10 of a milliliter. So that should be 20 milligrams per liter times 0.1. That puts me at, what would that be? 2 milligrams per liter, or less than 2, I should say, because it's not quite a full 1/10 of a milliliter. So that'd be less than 2 milligrams per liter of alkalinity as calcium carbonate. That is nothing. That is really, really low alkalinity. So this water is highly susceptible to pH changes if an acid is added or removed, or likewise if a base is added or removed. There's really no buffering capacity in this water, and that's highly reflective of the type of sediment that we have out there. Mostly quartz sand, and quartz sand doesn't really have many cations or things like bicarbonate that will leach out of it. So it's a highly stable aquifer, in other words, from a solution or dissolution perspective. So alkalinity is done. Speaking of dissolved carbonate and dissolved ions, there is another measurement that I want to make that will tell us more about not the anions, not the carbonate, but more about the cations. In particular, the concentration of dissolved divalent cations. Di meaning 2 and valent referring to the charge. So these would be ions that have a charge of +2. So positively charged cations. These will be, for instance, your alkaline earth metals. So calcium, magnesium, etc. The measurement for the concentration of dissolved divalent cations is known as hardness. So you may have heard of hard water, soft water before. Really all that is referring to is the amount of divalent cations in your solution. Mostly calcium and magnesium, but sometimes iron can be divalent. It can have a charge of +2 if you're in anaerobic conditions. So that can sometimes lead to hardness. Why do we call water hard if it has a lot of divalent cations? We'll have a lot more to say about this in the lecture, but the divalent cations are going to interfere with things like soaps, and they cause your soap to form insoluble precipitate. It's soap scum is what we call it. Also, some of these divalent cations will combine with carbonate, for instance, and they'll come out of solution and form a scale or a precipitate around your pipes. So long story short, you'll have things crystallizing in your pipes, and that's hard to work with, which is where the name hard in hard water comes from. Now, I've mentioned before, we have very good water here in Mobile, and as it turns out, our water that comes out of the tap, if you're getting it from Big Creek Lake, or if it comes out of the tap and you're getting it from groundwater, tends to be very soft. So there's no surprise we should expect our water from the Glen Sebastian Nature Trail to be very soft as well. There's no source of divalent cations. There's no rocks that we're dissolving that are releasing magnesium or calcium. If we had some limestone, we could release calcium in the form of calcium carbonate. If we had some dolostone, we could release calcium and magnesium from the dolomite mineral. But we don't really have any of that. We just have quartz. So I'm going to go ahead and pull this out. pH probe is done. I'll put the cap back on. I'm done with it. And in fact, I'm done with this sample. It's already been modified. So we've basically destroyed this fraction of the sample, but fortunately I have a lot more. And I'm yet again going to measure out 50 milliliters. There we go. So 50 milliliters to the bottom of the meniscus. I'm going to yet again put this sample into a clean beaker with a spin bar in it. Pour my water sample in there. And the way that hardness is measured is very similar to the way that alkalinity is measured. I'm going to do a titration. So what I'm going to titrate with is, I'll spin it around, this chemical compound called EDTA. Now EDTA has a very long name, but essentially what it is it's a chelator. A chelator is simply an organic compound that binds itself around certain dissolved ions. And in this case, EDTA will bind itself around divalent cations. So it basically, to me, it looks like a little Pac-Man molecule, and that's where the word chelator comes from. Chela means claw, and it will claw itself around divalent metals. So magnesium, calcium, and also if we have any iron too in our sample. Now, when it does that, it's going to basically bind up all the divalent metals in there. That on its own is not really any indication of anything. But if we add a little bit of buffer, so this is essentially a pH buffering solution that helps EDTA do its job. It's actually a form of ammonia. I should be doing this under the fume hood, but since there's no students, it's just me. And I'm just doing one sample, it's not an issue. Okay, so I've added my pH buffer. What I'm going to add that really tells us the change of divalent metal concentration is I'm going to add this solution called Eriochrome black tea. And Eriochrome black tea is a dye that has a small +2 charged titanium cation bound to it. And as long as that titanium is bound to this Eriochrome black tea, it's going to have a purple color. Okay, so I'll turn this on, I'll spin it up. I'm not worried about CO2 here. So there you see. Got a nice kind of pinkish color. I could make it darker. You got to be really careful with this stuff because it's kind of like the PVC primer. It will stain anything it comes into contact with. It's a very strong dye. But the cool thing about Eriochrome black tea is that if I pull away that titanium ion, the +2 titanium ion, this will change its color. And in fact, it's going to change its color from purple to blue. So if I add EDTA, what it's going to do, my little Pac-Man molecule, is first it's going to bind to all of the dissolved cations, calcium, magnesium, and iron. After it's freed up all of those dissolved ions, it's going to start to attack the Eriochrome black tea, and it's going to pull the titanium out, and when it does that, you'll see the color will change. So I just have to titrate with EDTA. For every milliliter of EDTA I add, that's the equivalent of 20 milligrams per liter of dissolved calcium carbonate, or limestone if you want to think about it that way. So the same exact thing for alkalinity, just a different titration, a little bit different setup. So I expect this to be very soft. Yet again, I need to keep really close eye on this titration. So I'll try and get out of your way so you can see. We're just going to look for a color change. Okay? So I'm starting at 0 milliliters with my burette. I'm just going to barely open this. Barely open. Not quite. There goes my first drop right there. See a small color change and then it returns. So let me add another drop here. Okay, look at that, color's getting a lot deeper. It's going from this reddish pink to a dark purple, which to me tells me that I'm getting some blue in there. That's going to shift the color from red to more of a purple color. Now I'm very close to completing this titration. Add one more drop. It's purple, deep purple, and just about the color that I'm looking for, but I bet I can do a little bit better and add just one more drop here. There we go. Now the color is blue. It's a cobalt blue. And at this point, this cobalt blue indicates that all the Eriochrome black tea has been consumed, or the titanium has been pulled out by my EDTA. In other words, I've titrated all of the divalent metals out of this solution. So how much EDTA did I have to add? Well, it turns out I had to add 0.2 milliliters. So same thing, we multiplied the volume that we added by 20 milligrams per liter as calcium carbonate. So 0.2 milliliters times 20 milligrams per milliliter as calcium carbonate. That would give us a hardness of 4 milligrams per liter as calcium carbonate. I'll go ahead and tell you, that's about as soft as water gets. I mean, that is extremely soft water. So if you ever complain about the quality of water in Mobile County, trust me, it can be a lot worse. If you go to Florida, the hardness might be over 200 milligrams per liter as calcium carbonate. That is insane. So you're working with very hard water in that situation. Whereas here, where we don't have limestone rocks, extremely soft. And it's kind of interesting, I've noticed several differences in the way that water tastes, in the way that soap works, in the way that even your hair will be shaped as a result of changing hardness. And again, it's pretty interesting. So this sample is consumed, all done. I'm going to turn this spin bar off. The last thing that I want to measure is I want to get an understanding of how much dissolved solute is in this sample, regardless of whether it's alkalinity or hardness or pH or something like that. I just want to know how much salt is in there, how much is dissolved in there. So one quick and easy way to do that is to measure what's known as the conductivity, the electrical conductivity. The more salts are in the water, the more electrically conductive it becomes. Well, I've got a simple probe here, a conductivity probe. And you can see, really the way this works is we've just got 2 electrodes there. And we can measure then, if we apply a voltage across these 2 electrodes, we can measure the current that passes through, and based on Ohm's law, we can calculate the resistance of this sample. Well, if we know the length between the probes, we know the cross-sectional area of the probes, we can calculate the resistivity, take the inverse of it, that's the conductivity. Now, typically when you're measuring conductivity, we may keep track of what are called mhos. That's a unit of conductivity. It's basically ohm spelled backwards. But a lot of times, we just convert a conductivity over to what's known as a salinity. And that would be an indication of the dissolved salts in a sample. So it's based on a standard curve. So I'm just going to read out salinity directly. And it gives us an idea of the mass of dissolved solute per volume of sample. So I'm going to drop this in here. This will tell me salinity in parts per thousand, which I really don't like that particular term, but it's another way of saying parts per thousand would be in grams per liter. And this actually says, get this, it says 0.00 parts per thousand. So that would be less than 0.00 or less than 0.01 parts per thousand or grams per liter, so less than 10 milligrams per liter. That is very fresh water. Okay, there's really nothing dissolved inside of this. So this water is very high quality. I'm going to go ahead and write down concentration less than. Note I don't put 0.00, but I put less than my smallest measurement or my detection limit of this instrument. So less than 0.01, and that would be in ppt by mass. That's grams per liter. Okay, so essentially nothing. Very fresh water. So this water is ultra pure. I mean, it's great. We have great groundwater here. It's a good resource. The only thing that I would be concerned about in the shallow groundwater would be if there's any sort of dissolved contamination from the land surface. So if you're using any herbicides, pesticides, maybe you spilled some chemicals, then that would quickly get in the water. It will not show up necessarily as dissolved ions. So conductivity may not pick up dissolved organic contaminant or contamination. The other thing I might be concerned with would be pathogens. If you're working with a superficial aquifer, then if there's any sort of discharge of, let's say, human waste or excrements, or maybe pet waste, or maybe even livestock or wildlife waste, then you have to worry about certain pathogens like fecal coliforms getting into your groundwater. That's something that we have a lot of concern when we talk about developing nations where they have shallow groundwater wells. people gather around the wells. That's also where they tend to use the bathroom, and that can cause some serious human health issues. I will tell you, I've tested the water from MW2 several times for fecal coliforms and for other pathogens, and I've never detected anything. So this water, in my opinion, is about as good as it gets. This is really good water. So I'm still alive. I've been drinking this for years and years, so maybe if I pass away, there's something in here that I haven't tested. So I'm doing a human toxicology test, but I'm actually, since I've got this water sample, I'm gonna put the cap on it, I'm gonna bring it home, and I'm probably gonna drink on it for the rest of the evening and the rest of the weekend. So that's it for our data collection. I've got all the data in hand here. The real focus of this lab is to take this information and use it to help us determine the best course of action for removing your contaminant from the groundwater. So it'll be up to you as your group to select your contamination, or contaminant I should say, talk about feasible remediation strategies, and I'll give you a table to help with that, and then decide on which one to use. So I'm allowing you to produce your results in 2 different formats, depending on what you guys choose as a group. You can either write me a report, and I'll give you the details of it, or you can give me a live oral pitch. So you could give me a presentation over Zoom, basically describing the same thing you would put in the report. Okay? So I will see you guys back inside the classroom for lecture, and I'll also have some more to talk about in the board about this project. So take it easy.